Welcome, friends. So, we are discussing network theory. Previously, we have discussed the AC network applied or AC signal is applied on various components like resistance, inductance, capacitance, or maybe combination of any two. So, we have seen many important aspects there, just like that in case of a resistance, voltage and current phasors are in phase. In case of a inductance, current is lagging 90 degree than the voltage phasor, and in case of a capacitance, current is leading by 90 degree than the voltage phasor, and thereby we have got a very important relation that power which is equal to VI cos phi, and from we have got the idea of power factor. It is the cosine of the angle between voltage phasor and current phasor, where the frequency of the voltage and current signal must be the same. So power factor, the value of power factor ranges from 0 to 1 depending on the value of resistance, inductance and capacitance. If the AC network is dominated by resistance, then power factor is most likely to be tilted towards 1. And if inductance or capacitive value is dominant over resistance, then the value of the power factor is most likely to be tilted towards 0. If the circuit is inductive, then the power factor will be lagging in nature, and if the circuit is capacitive, then power factor will be leading in nature. So this much we have seen previously. Now today, in this part of this lecture, we will see the another one aspect which is called parallel AC circuit, which is parallel AC circuit. Now this parallel AC circuit, before discussing this parallel AC circuit, let us investing some time on power factor. And what is this power factor? And power factor influences in how many ways in voltage and current? Let us say we have a fundamental relation. We have P is equal to VI cos phi. Now, having said that, we know the ranges of power factor is from 0 to 1. Now it is worth searching that what range, actually that means what value of power factor is good for our electrical system, whether if the power factor stays near 0, is it good, or power factor value closer to unity or 1, it is good for our electrical system. Let us understand this aspect, because power factor is totally dependent on load or RLC. Power factor is totally dependent on R, L and C. So from the impedance triangle we have seen that R, this phasor, horizontal phasor is R, vertical phasor is J omega L, and this phasor, resultant phasor is Z. This angle is phi, so tan phi it will be J omega L by R. So from there we can calculate cos phi, that is equals to r by z, and where z is equal to root under r square plus omega square L square. So the cos phi, that the value of power factor is dependent on R, L, and if it is a capacitive circuit then C will come into the picture. So the question is, what value of capacitor is good for us? Is it the power factor value closer to 1, it is good, or it is closer to 0, it is good? So let us investigate this issue, because it will be very important to know actually. So from here we can write I, that is equal to 1 by cos phi if P and V are constant. Okay, P, let us consider this fact for the time being. Active power and voltage are remain constant. So from this expression we can say that current is inversely proportional to the power factor. Current is inversely proportional to the power factor. So now from this result what we can observe here is that if cos phi or power factor is less, if cos phi is less, the immediate conclusion is what? I will be more. So now there is a problem with this more current. There is a problem with this more current. What is that? The first problem is that if a conductor carries a current of 5 ampere, if a conductor carries a current of 5 ampere, and if a second conductor carries a current of 50 ampere, so naturally the cross-sectional area of these two conductors are not same. So A1, if this is A1 and if this is A2, the current 50 ampere conductor, the cross-sectional area is A2, and the first area of cross section of the first conductor which is carrying 5 ampere, it is A1. So naturally A1 less than A2. So if current is more, immediate conclusion we can draw from here is that we require more copper. We require more copper or aluminium as a material of the conductor. So what will happen to this, that if we require more material, that means cost will increase. So that is the first drawback. Having power factor is of low value. So if power factor is less means it is closer to 0, then immediate conclusion from here is that current will be more from this relation, as it is inversely proportional to the power factor. If current is more, then we require it. Immediate conclusion we can draw from here is that we require more copper or aluminium as the material. Therefore, the cost of the material will increase. This is number one drawback. The second issue is that if current is more, that immediate conclusion is that I square R, that means it is called power loss. I square R, it is called power loss. The power loss will be more. So if the power loss will be more, then overall efficiency of the system will reduce. That is another drawback. So if the current is more, then power loss will definitely be more. So as a result, overall efficiency will reduce. Again, another issue can be said like this: if current is more than IR, that means potential drop. Potential drop or simply voltage drop. Voltage drop is more. So what will be the immediate effect is that if voltage drop is more, the voltage regulation will reduce. Voltage regulation will be reduced. What is voltage regulation? Suppose we have a sending end voltage Vs and we have a receiving end voltage Vr. This is S for sending end, R for receiving end. The voltage regulation is given by Vs minus Vr, this difference. If this difference is less, the more it will be less, or this difference between sending end voltage and receiving end voltage, the lesser this difference, the better the system is. That means if Vs and Vr is lesser, then our system performance will be better. System will be better. So with this we can clearly say that if in a practical or in a electrical system, if that system is operated with the low power factor, if that system is operated with the low power factor, then this problem will surely arise. These problems will arise definitely. First of all, the conductor will require more copper material, so conductor pricing will be increased. Conductor loss, that means power loss in the conductor will be more, that is mean efficiency will be reducing. Okay, and thirdly, IR drop, that means voltage drop will be more, therefore voltage regulation will be reducing. So these problems will creeping in to with the lower value of power factor. So if a electrical system, if a system operates at a power factor of 0.56 lagging, let us consider one rough value, 0.6 lagging. So it is always expected to lift this power factor near to unity. So we can try to bring this 0.6 power factor to 0.7 or maybe 0.8 or maybe 0.9 or maximum to unity. So if we can do that, then if we can improve our power factor, then these things will be mitigated. That means if power factor is more, then current will be less, conductor material will be less, so cost will be reducing. If the power factor will be more, current will be less. If the current will be less, then power loss will be less, then efficiency will be more. And similarly, if the current will be less, then IR drop will be less, then regulation will be more. So if we can make our power factor from any value, if we can increase that value nearer to unity, then it is a good for our electrical system. So that is why we always make an attempt to improve our power factor, to improve our power factor. Improving the power factor means it is to bring the power factor from low value to high value. Low value means near to 0, high value means near to 1. So let us say we have a power factor operated on 0.6 lagging. So we need to bring this power factor to 0.9 lagging. So in this way, just for a rough example, in this way, if we can improve or if we can increase that power factor, then it is surely for betterment of our electrical system. So with these fundamentals or with this background, we shall go to the parallel AC circuit. We have a first, let us consider series RL circuit. This is resistance and this is inductance, and the current flowing through this RL, it's called I coil. This current is called I coil. And let us connect a capacitor in parallel. Let us connect a capacitor in parallel, right? This is a capacitor in parallel. Now, for the time being, let us consider capacitor is not connected. For the time being, let us consider capacitor is not connected. So now if I try to draw, now it is an example of series RL circuit. It is an example of series RL circuit, right? So current flowing through, as it is mentioned, it is I coil. And voltage appearing across coil is V. Voltage appearing across coil is V. So the phasor diagram would be like this. Phasor diagram would be like this. So if V is this, that is the supply voltage, then I coil. Okay, let me make more space. So if this is L, if this is supply voltage V, so this must be I coil. It will be lagging by some angle I1. Okay, so this is the I coil for us. This is the supply voltage V. Now with the inclusion of capacitor, now if a capacitor is connected, now let us say capacitor is now connected. Okay. So what is happening here is that it starts drawing a current that is called IC. It starts drawing a current, it's called IC. Now since capacitor is alone present, then this charging current from the rule of the series C circuit, which has been discussed previously, this IC must be leading than the voltage 90 degree, which must be leading than the voltage 90 degree. So this is the phasor IC, because current IC, it is current flowing through the capacitor alone. So whatever voltage appearing across the capacitor, which is V, so this IC and V, the phase relationship between them is this, that is the charging current or capacitive current is 90 degree leading than that of voltage. Now the phasor summation of this I coil and IC becomes the supply current. So this supply current I will be the phasor summation of I coil and IC. So now if you draw in reverse direction IC, let us IC is this. Okay, let us say IC is this. So I coil plus IC, that becomes I coil and IC, that becomes total supply current I. So here it is. So this phasor, So this phasor actually the I coil, right? This phasor is I coil. Now this is IC. This phasor is IC, which is 90-degree leading. Now this is drawn here. So phasor summation of IC and I coil, phasor summation of IC and I coil is the supply current I. So this phasor. So this phasor is I. Now what happens to this is that you see the initial angle was phi 1. The initial angle was phi 1, this angle. Now with the inclusion of capacitance, the angle now reduces to phi 2. Angle reduces to phi 2. So naturally phi 1 from the phasor diagram, phi 1 greater than phi 2. So naturally what will happen here is that cos phi 1 is less than cos phi 2. So we have a very important observation from this is that when a capacitor is connected in parallel to this coil, what is happening actually from this equation? What we can understand? We increase or we improve our power factor effectively. We improve our system power factor effectively. Now you see this cos phi 2 is the new power factor which is greater than previous power factor. Previous power factor means what? When capacitor was not connected. The cos phi 1, the power factor when capacitor was not connected, right, was not connected. However, this cos phi 2, that the new power factor with C connected, with the capacitor connected. So what conclusion we can draw here is that if we add a capacitor in parallel to the coil, effectively we can improve our power factor. That is a very important fact. So that is the one of the characteristics of parallel AC circuit. If parallel AC circuit, the original topology of a parallel AC circuit may be different. It is one of the forms when RL in parallel with C. This is very important because of this reason. If we add a capacitor in parallel, then overall power factor of the system will be improved. So let us quickly recap why improvement of power factor is necessary. We have already discussed this. If P and V are constants, then low power factor causes to draw high amount of current from the supply mains. So what will happen? Immediate conclusion, what can be drawn? If I is larger, then it requires conductor with larger diameter to carry excess current. Hence, cost of the conductor will increase. This is number 1. If I is larger, then I square R loss will be more. Hence, efficiency of the overall system will reduce. This is number 2. And 3 is if I is larger, then IR drop, that is voltage drop, will be more. Therefore, voltage regulation will be poorer. Now, it is quite interesting that if we add a capacitor, then the power factor will be improving. That's amazing. But what does capacitor do? What is the relationship with the power factor of that capacitor? And why power factor improves with the inclusion of the capacitor? What is the reason? Now you see, the by virtue of nature, electrical system is always inductive in nature. Always inductive in nature. Now let us means here equation 8. What is equation 8? Let us find out. So this is the equation 8. You see this equation 8, that is instantaneous power is 0 in case of an inductor. This is equation number 8. Instantaneous power is 0 for an inductor. So power consumption or power dissipation through an inductor is 0 from the equation 8. However, it absorbs reactive power. It absorbs reactive power. Already mentioned, if an inductor is there, it absorbs reactive power. This is called lagging var. On the other hand, C, what does C capacitor do? C delivers reactive power. C delivers reactive power, which is called leading var. Now what is the formula for Q? Q is equal to VI sin phi. Now you can understand one thing: inductor absorbs reactive power and capacitor delivers reactive power. Now these two reactive powers are, opposite to each other. One is absorbing, another one is delivering. So there, if you consider this leading Q as a positive var, then lagging Q must be negative var. So they are opposite to each other. So this is the reason on inclusion of the capacitor, it either partially or fully neutralizes the lagging var. That means, what does this statement mean? Whatever be the requirement of this inductor, it is taking reactive power, right? It is taking reactive power, whatever its requirement. If you put a capacitor in parallel, then it will deliver that reactive power. So in this way, this reactive power either partially or fully neutralized by this capacitor. So the burden on the supply is reduced. Burden on the supply reduces. On before capacitance, it is drawing reactive power from the source. It is drawing reactive power from the source. However, when capacitor is connected, it is drawing reactive power from that capacitor is now delivering. So the burden on supply reduces. So due to this reason, the effect of resistance increases. Since the burden on supply reduces, it is now starting taking reactive power less from the supply. So the effect of R, that is the overall resistive effect, increases, and hence power factor approaches to unity. Lastly, power factor for a purely resistive network is it's always unity. So we have seen this fact. So this is a parallel AC circuit, one of the forms of AC circuit where it is extremely important when this R and L are connected in series. Then with that, if a capacitor is connected, this entire assembly, you can think that a power factor improvement circuit, power factor improvement circuit. So in this talk, we have discussed what is power factor, what should be the ideal value of the capacitor for a good power system or good electrical system. We found that power factor should remain closer to unity to get several advantages. So therefrom we have seen, or we have analyzed one AC network, that is parallel network, where a capacitor alone is presented or connected in parallel to a coil which consisted of a resistance and inductance. There we have seen that if a capacitor is connected parallel to that, then power factor of the overall network is improved to a substantial amount. So whenever we have low value of power factor or poor value of power factor, a capacitor should always be connected in parallel to the load so that it delivers some reactive power, so that the reactive power requirement, that is the inductor, the reactive power requirement of the inductor either partially neutralized or fully neutralized or fully met. So in this way we can improve our power factor. So with this we are ending this part here. From the next class we will solve some problems on series and parallel AC networks. Thank you.